Alright, we're back at section 3.3. We're going to attack two different topics, but they're, excuse the pun, but they're related. I've already sent you a link to a video on the implicit differentiation. I hope you enjoyed Nancy Pye telling you about how to do implicit differentiation. But we'll get a little bit of a review here, then we'll look at some related rates. It's actually pretty easy once you get the hang of it. So first of all, get my pen going here. There we go. There's our pen. Alright, implicit differentiation. X squared plus y squared equals -1. The different thing about this is the y squared. Up to this point, we've typically had a y equals something. Now we've got y squared. Even if we solve this for y squared, we'd have some difficulty. But implicit differentiation takes care of that. We don't need to know the explicit one. We can still find dy dx. So that gives us a lot more power. Here's an equation, for example, and since we want dy dx, we're going to differentiate this implicitly. Now the important thing is to be a true aficionado of the chain rule, using it almost where you don't need to. That will make implicit differentiation second nature. So first of all, we'll start out with the original equation. And we're going to differentiate, but all the way through we're going to think about the chain rule. So if I look at this first one, x squared, we've got an x inside. The x, remember, itself can be considered a function. We're going to look for dy dx, so we're going to differentiating with respect to x. So our derivatives will have dx in the bottom. Keep that in mind. So the easy part is the 2x part. If you consider x as like a function itself, then we'd have dx, and since we're differentiating with respect to x, it would be over dx. Well, that looks like it should be 1. It is. But I want to get you in the habit. So in the second one, take the simple derivative of this, you get 2y. But if you think about y as a function, we'll have dy and dx because we're differentiating with respect to x. On this side, the derivative of 25, 0 easily. Next, since this is a 1, we can just write this as 2x equals 2, plus 2y dy dx. You can write that as y prime if you're real careful. Next, we want dy dx, so we'll subtract 2x from both sides, and we'll have 2y dy dx equals minus 2x. Just like an ordinary equation, divide both sides by 2y, and now we'll have dy dx equals, and you'll have a 2 on the top and the bottom, so you end up with minus x over y. And there's your derivative. But we're not quite done, because it says evaluate the derivative at these 2 points. Actually, this is really easy. So you want dy dx for the first point. Just put the value of x from 4 to 3, that's a 4. Put the y value down here, and there's your derivative. at the point 4, 3. You want the other derivative? No problem. dy dx equals, now you want it for 0, 5. So negative, 0 goes on the top for x, 5 goes on the bottom for y. The derivative is 0. Very simple. Let's clear that so we can get that little review. Solve that for dy dx. Cancel out the 2's. And we've got our derivative. And then we'll go back and pick up the points. So this is their new notation for getting the derivative at this point. So put the 4 in where the x was, the y in where the y was, and there's your derivative. Same thing over here. Put the points in for the x's and y's. And there's the slope of the tangent line for the circle, 4, 3. And, oops. And we already have the slope of 0. Okay. Next. This one has y cubed. That makes it more interesting, shall we say. We want to find dy dx. Notice that when I take the derivative of this, I'm going to have to use the product rule. Same thing with this one. Of course, that'll give us 0 when we take the derivative, and another 0. So, let's take the derivative of this. Let's set it up. X times the derivative of y plus the derivative of x times y. Product rule for the first one. Now, product rule for the second one. X squared times the derivative of y cubed, there, plus, reverse the roles, the derivative of x squared and y cubed. And if we added the 1 to both sides, we'd have a 1 on the right side, but the derivative of a 1 would be 0. Let's see what we've got now. The derivative of y, remember, we want it with respect to x, so this will be x dy dx plus the derivative of x is dx dx, or 1, times y, or just a 1, plus x squared, take the derivative of y cubed, that's 3y squared, so put the 3 out here, 3y squared, and the derivative of y itself is dy dx, plus the second part of the product rule, we've got the derivative of x squared, it's 2x, and just y cubed for the second part of that term, equals 0. Now the key here is we want dy dx. So we're going to keep the terms that have dy dx on the left side, move the other ones to the right side. So I've got x dy dx plus, take the second one that has a dy dx on it, 3x squared y squared dy dx, and I'm going to move the y to the other side, so I've got a minus y, and the 2xy cubed to the other side, Now the key here is, once you've got the dy the x terms over here. We're going to factor that out. dy dx. Factor it out like you would any normal factoring. X plus 3x squared y squared equals minus y minus 2x y cubed. And just as if we had a times dy dx equals something, we'll divide that. So we'll divide both sides by this term. So we'll get dy dx by itself. And on this side, we have this. And we divide both sides by x plus 3x squared y squared. And there's our derivative. All right. Let me clear this so you can see the workings of it again. Both those are products, so we use the product rule twice. So we set it up, derivative of the left side, derivative of the right side. Split them up into their individual terms, take the derivative of that. In other words, divide and conquer. Next, use the product rule. Here's the x and the derivative of the y. We've got the y and the derivative of the x. Remember, we reverse the roles. On the other one, x squared times the derivative of the y cubed term, and then reverse the roles. And this is the derivative, and this is the original. Multiply that out, and this is what we've got. And we're going to isolate the dy dx terms, this one and this one, and then factor out the dy dx so we can solve for it. Divide both sides by the x plus 3x squared y squared, and there's our derivative. Moving along, we've got another one to work on. We're looking for dy dx. We don't have the y term itself, so we have to use implicit differentiation. So here we are, write down on our paper, change that to exponents that we can work the power rule with, and take the derivative of both, which we can split up. Take the derivative of each term individually, bring that 1/2 out front on the first one, reduce the power by 1, so we'll have 1/2 x to the negative 1/2. Notice this is the old exponent, this is the new exponent, old exponent, new exponent. And since we're taking them with respect to x, and we don't have a d anything on this one, we do on this one because we're taking the derivative of y with respect to x. Now we moved the first term to the right side because this is the term that has the dy dx. We want it isolated. Then what we'll do is we'll take the coefficient of that dy dx term and divide both sides by that. And that gives us dy dx. And we've got some negative 1/2 on top and bottom, so they cancel out. So we have x to the minus 1/2. over y to the minus 1/2. And since those are negative exponents, that means bring this one down to the bottom with a positive 1/2, and bring this one up to the top with a positive 1/2 for an exponent. And there is your dy dx, which you could also write, if you chose to, as the square root of y over the square root of x. Or you could combine them, put them both under one radical. It all depends on your situation, which one is more convenient to use. Now we get to some examples. Now it gets to be even more fun. That wasn't too bad, was it? Get some practice, make sure you're good at this. You might even want to pause it here and try 1, 2, 3, up to 5 different implicit differentiations, and come back here at slide 13. So how does this go? Well, first of all, you've got a sphere. Our balloon's a sphere. We're being a perfectionist here. Won't be exactly a sphere, but close enough for our work. So we're talking about this sphere getting bigger and bigger, and at the same time it means this radius is getting bigger and bigger. So we've got some numbers in here, and what we need to do is put these things together. So it says here that you're getting air from the compressor at a rate of 2 cubic inches per second. Now you can almost figure out what this is. This is a volume, it's cubic inches. This is a time in seconds. So what this represents is how the volume is changing over a unit of time. So you've given us that the volume is increasing at 2 cubic inches per second. What else does it say? It says how fast is the radius growing? We'll get back to that. And the radius is 3. So radius equals 3 inches. Here's another piece we've got. What we want is how fast is the radius growing? The radius growing, what is changing is the time. So what we want is how fast is the radius changing as time is going by. Here we go. The other thing we need is what is the connection between V and R. Well, this one you can find in a table somewhere. The volume of the sphere is 4/3 pi r cubed. Are you expected to know that? No, that's probably not in your memory, but it's something you might use for a while right here. So you might want to put that in your memory bank, or at least your semi-long-term memory bank. Now we know that we're going to be talking about how the volume is changing over time, so we're going to be differentiating this volume formula with respect to time. dV dt. It's not dx as we've used quite often in the past. So the first one is easy. V, the derivative of that is 1, and since V is actually a function, well, 1 dV dt. Here's our implicit differentiation. Over on the right-hand side, notice that 4/3 and pi, as a package, are all one big constant. So let's keep it by itself. But we do have to differentiate the r cubed. So we'll bring the 3 out front, reduce the cube by 1. Now, we're differentiating with respect to time, so we have to think chain rule. So since it isn't time, it'll be dr dt, which represents how fast the radius is increasing per unit time. And there's our formula. The first thing we might want to do is notice that we've got a 3 in the denominator here, a 3 in the numerator there, so those two can cancel. So you could write this as dv dt equals, since the 3's cancel, we'll have 4 pi, that's a constant, times r squared dr dt. Now we'll put in our numbers that we stacked up here. We're working our problem with respect to these two parameters. So dv dt is 2. So put 2 there. Excuse me. Equals 4 pi here. R, said it's going to be 3. That's the one. That's what we're interested in. Don't forget it's squared. dr dt. Okay, so what do we have? We could divide both sides by 2 real quickly. So we'd have 1 over here, and we'll have 2 over here, and this is r squared, that's 81, times the 2 is 162 pi, 81 times 2, dr dt. Solve for dr dt. Divide both sides by 162 over pi. dr dt equals 1 over 162 pi. What? Well, we can just look back here. What's the radius? Well, it's in inches. Inches per, and this is time, second. This means that the radius is expanding at 1 over 162 pi inches per second. Clear our ink, and here we go. So put down what you know, what we want to find. And there's a formula we need to use. Start with that equation, or that formula. We're going to differentiate both sides. Remember, 4/3 pi is a constant. So dv dt, and that 4/3 pi is a constant, so we'll keep that out there. Differentiating with that 3r squared, those 3's will cancel. So our dv dt is 4 pi r squared dr dt. We know what dv dt is. We know what our interest, r of interest is. So we'll put those in. Oops. I don't get that. Guess I made a mistake earlier. Should have been 3. My mistake. So we'll get 2 over 36 pi instead of 2 over 160 something or whatever, 162. So radius is increasing at 0.018 inches per second. Still pretty small. Not as small as I had there for a second. Next, let's look at an airplane flying in a circular holding pattern. They give us the equation of the path of the airplane, and there's a particular place we're interested in for the plane. And the plane is at square root of 3 miles. Sorry about that, it's about 1.732, but this makes it a little bit easier because of this. It's easier to tell how that goes together. So the plane is right here, 1.73 miles east and 1 mile north. The question is, when it's at this point, how fast is it going west? So we differentiate both sides of the equation, and we're going to use our implicit differentiation. Split those up according to the sum and difference rule. Do the differentiating. Notice that the 2x is times dx dt because we're not differentiating with respect to x anymore. We're differentiating with respect to time, which usually is in the case when we're talking about rates. So there's our derivative. Go back through here, make sure you can get from here to here. Now, since we want dx dt, we're going to put these numbers in, and dx dt is the only part that we don't know. We're going to have to work with all those things carefully and solve that for dx dt. So bring that 2 times 1 times 300 to the right side of the equation, and then dividing by 2 square root of 3. We can reduce that a little bit, which gives us this, and that is our solution for dx dt. So this is how fast in the west direction, notice it's a minus, and we're talking about dx dt, so that means it's going west as opposed to east. If this were positive, it would be east. And that gives us a value, an absolute value or amplitude for how fast it's traveling west. Now we've got a bit of a similar one. We've got a picture here, but I'm not sure that it's terribly useful, but it does get us off to a start. So car A is half a mile from the intersection, moving south at 60 miles per hour. Oops, here we go. Take car A first. It's traveling east, so that's this car. It's going in this direction, and it's half a mile from the middle of the intersection. Car B is 0.75 miles away, and it's traveling toward the middle of the intersection at 60 miles an hour. 40 miles per hour here, 60 miles per hour there. From the figure, we can write it like this. If we look back here for a second, if we want to, if we draw this picture, we've got car B up here, we've got car A down there. Don't worry about whether it's to scale or not. We want to find out something about the distance between the two cars. The distance between the two cars is this part right here. We'll call this S. Since this makes a right angle here, we can use the Pythagorean theorem. So S squared equals x squared plus y squared. We'll differentiate with respect to t because t, or time, is what's changing. So we'll take the derivative of both sides, use the sum and difference rule, and take the derivative. Remember, each one of these is with respect to time. We want ds dt, so we divide everything by 2s, sort of like this. Notice that the 2s down here, the 2 is going to cancel out. Remember, this 2s is divided into both of those, not just one of them. So this is what we get. And then we're going to start putting the numbers in. So the x direction for car A, it's 3/4 of a mile away. We'll put that in here for x, right there. We'll put the 0.5 in for y, which is right there. We know the speed of car A. We know the speed for car B. We'll put both of those in. Speed of car A, speed of car B. We also need to know the distance between them at this particular point. Remember, the picture looked something like this as the cars were approaching the intersection. So here's S, here's X, here's Y. We can find this because we've got 0.75 here. I've got it right. Oops. And 0.5 there. And we can get the square root of 0.8125 using our calculators. So the cars are right now 9/10 of a mile apart. We'll put all those numbers in there and find out how fast the cars are either getting close to each other or going further apart. Put all those numbers in, engage with our calculator, and we got negative 72.2 miles per hour. Why negative? Because the cars are getting close to each other. 72.2 miles per hour. Next, we've got something that I'd never heard of before, and very likely you haven't either. Don't ask me anything about this. I'm just taking the formula as it's shown, but we can work this anyway, even if we don't recognize this as something we've worked with before. The Cobb-Douglas production formula. If you're interested, check with Mr. Google. I'm sure you can find something about it. So P is production level, X is units of labor, Y is units of capital, and C and A are constants. A is between 0 and 1. That's important. It's between 0 and 1, which makes sense because this is 1 minus A. So And those two exponents together, if we added them together, would give us 1. So I'm sure there's some significance to that. And the c is just some constant, probably for the particular application we're interested in. So here we go. Here's our basic equation. And back here, where is it? Okay. It says currently it's using 16 units of labor, 81 units of capital. Labor is increasing by 4 units per month. What does the change of units of capital have to be to maintain the current level of production? Well, this is important. Maintain the current level of production. So that P that we get, we can put those numbers in and find out what we've got. Production, just put it in there. Put our calculators to work. Or actually, this will work with our heads too, because 16 is a perfect 4th power, and 81 is a perfect 4th power as well. So the production level is 1,080 units. We want to keep that 1,080 units constant. So that means 1,080 equals 20 to the 1/4 times y to the 3/4. And if we divide both sides by 20, we can simplify it just a tiny bit. 54 equals x to the 1/4, y to the 3/4. Time to use implicit differentiation. So here's the left side. That was the level of production. That's 54. We know that's going to give us 0. X to the 1/4 is the first part of our product. We'll keep that the same. We'll differentiate the second part of the product. Then we'll reverse the two roles. Y to the 3/4 and then the derivative of the x to the 1/4 by the product rule. Cleaning up a little bit, there's a 0. We'll take the derivative of those two terms. The chain rule is going to give us, so we'll have x to the 1/4, bring that 1/4 out front. So we'll have 0 equals x to the 1/4, the 3/4 y, negative 1/4 there. Remember, subtract 1 from our exponents when we use the power rule. Don't forget that. So for example, this becomes that, and so on. Now, we already are given these, so all we need to do is substitute in those. Now, it looks a little bit messy, but those things clean up very well. And using a calculator makes it child's play, actually. Put those all together, and what do we get? Well, we've got an equation with a derivative, and this dy dt is what we wanted. So we'll move that 27/8 to the other side. We'll divide both sides by negative 1/2, or multiply by negative 2. And there's our dy dt, negative 6.75. In other words, it's decreasing. Remember, these are calculus is all about rates. So we've got a rate that tells us the y's are decreasing. Since the negative, capital is decreasing at 6.75 units per month to keep the current level of production. Remember, that was 1,080 units per month. And that should give you a little bit of a start to implicit differentiation, which you should have started on, and some related rates too. And we'll come back with some more practice next time. Until then, I'll see you.